Let's do a problem with some cards in here, and let's head into it. Okay, so let's have a real look at this. So we've got 3 cards are drawn at random from a standard deck of 52 playing cards. Determine the probability of these following things. And we're going to have to do some work before we get there. So we've got 3 cards drawn, so that we're not thinking of a Venn diagram because we're not kind of intersecting probabilities here, but we're doing an event and then repeating it. So we're going to do one and then another and then another. So into your box. And so in this case, what it kind of looks like we'll need to do is rather think in terms of a tree diagram. Because we're going to draw something, so we're going to kind of draw the first card, and then once we've drawn it, we're either going to get an ace or we're not going to get an ace. Because all we're interested in, all our probability is ace, ace, ace. Do we get an ace or not? And then we're going to draw a second card, and we're either going to get an ace or we're not going to get an ace. And so it's going to go ace, not ace. And finally, we're going to draw a third time. And the third time we could get an ace or not an ace. Or we could get an ace. So, well, we'll interrogate this diagram in a second a bit better. So ace, not ace. Let's make sense of what we've done in a second. Okay, so out of all of this, if we traced along our diagram to see what we've done, we could draw an ace to start with, we could draw another ace, and we could draw another ace. So that would represent drawing 3 aces in a row. The only way we could draw 3 aces. Let's choose another path just for fun and say, let's say we drew an ace to start with, then we didn't draw an ace, then we drew an ace. So there we would have drawn 2 aces, but actually there's another way we could have drawn 2 aces, because we could also have gone ace, ace, not ace. Or we could have gone, let's go for a third one, not ace, ace, ace. So there are going to be various ways. So if we wanted to see how many ways are there of drawing 2 aces, well, there are quite a few different ways. Well, there are 3 different ways. We have to think about our probabilities a bit more. Okay. Now, the other thing we need to add to our tree diagram here is the probabilities of each of these things happening. Now, for my mind, what's a useful kind of strategy is to think, okay, well, when we first draw, there are 52 cards. So I'm just going to put over 52 over 52. And I want to think about that denominator to start with. Say, well, if we've withdrawn our ace, then the next card that we draw, there are only going to be 51 cards in the deck. So our denominator in each case here is 51. And maybe a point to clarify is, if you're taking your cards and you're drawing 3 at the same time, we can kind of think of that as drawing one, drawing another one, and drawing another one. Kind of works out the same, because when you're drawing all 3, it works out probability wise the same as kind of drawing one. Don't look at it yet, of course, and then draw the other one. Clearly, it wouldn't make a difference if you looked at it or not. So 51. Now in the last bit, we've got 2 cards out already. So our denominator here is 50, 50 all the way around. Now, it's kind of, I guess, does it feel like overkill or not? I'm not quite sure of drawing this whole tree diagram with all of these. Or maybe you could do some of these questions with the tree diagram in your head without having drawn the whole thing. I'd say let's draw it. It's useful to get into it like that. So now let's think about what these are. Well, how many aces are there in the pack? Well, there are 4, 1 from each suit, and therefore there are 48 cards in the pack that are not aces. Now, if we've drawn an ace, we've taken one of those aces, so there are only 3 left. So there are only 3 left. There's still all 58 non-ace cards there. Now let's keep going along this top branch. So if we drew an ace, and then we drew another ace, well, there are only 2 left out of the 50. And all 48 non-ace cards are there. Now, I'm really kind of overthinking this and thinking through it and writing down and talking about it slowly, just to make sure, we're probably doing that, but just to kind of pause and go through it rigorously, or not pause, just think through steadily and going, okay, well, we've drawn 1, so there are only 3 left at this stage. Then if we don't draw, well, there's still those 3 left at that stage. Now, that means that there must be 47. Thinking about it another way, we've drawn an ace, there's still 48 non-aces. So if we draw one of those non-aces, there must be 47 left. And so we can go along. Not ace, there are all 4 left in the pack. And if we let's think about that again. 48, which means we haven't drawn yet. So there's still all 4 aces left. We've drawn one of those non-aces, so there are only 47 left. If we go for a non-ace again, there are only 46 left over here, which means that if we draw not an ace and we draw an ace, then there were 4, now there are only 3 left. So our probability of that, there were 4 in that, we've taken one of them, which means there must be 47. Yep, that makes sense there. We've got 48 and we've taken one of them. And here, not ace, over here, 47, 46 left here, which means that over here, there 4 out of 50 are aces, right? Because we haven't drawn any yet along that branch there. Okay, clearly drawing the diagram a bit neater helps. Okay, so there's our diagram though. Now we just need to think about our parts. Now, I was going to say unfortunately, I think maybe it is a little unfortunate that to do these, we're going to be adding lots of things together. Remember, when you're going along a path, you're going to multiply, and if you're going to choose various different paths, you're going to add those probabilities together. So the first one says, probability of drawing exactly one ace. So let's just draw along our diagram to see where we go. We could have an ace. Now we've drawn our ace. So that's it. So we have to make sure that we draw not an ace and not an ace. Because we can't go ace, ace, then we got 2. Now what we could also do is one ace. If we had not drawn an ace, we could get an ace on the second one, but then we must not get an ace on the third draw. Or we could draw, and I'm going to just draw this below here. We could not draw an ace. We could not draw an ace and draw an ace at the end. Okay, so either it's ace, not, or it's not, ace, not, or not, ace. So those 3 things. So now we're going to multiply our probabilities along the way. So our probabilities are going to be, I'm actually going to do this below. Luckily, we can probably keep most of it in picture. To go for part 1, we're going 4 over 52 times 48 over 51 times 47 over 50. So that's that first path. Or we've got 48, we've got a not ace to start with, times an ace in the second go, 4 out of 51, times a non-ace in the last one, 47 out of 50. Or we go non-ace, 48 over 52. And then we didn't get an ace again, 47 out of 52. But we must have got one of those 4 aces remaining from the 50. And sorry, I see it. Maybe my login was in the way there. But 5150. So maybe just to double check, each denominator went down, right, as we went along. And into the, oh no, that's a rather large calculator. We don't need to see it that much. Oh, we're back to our cards. We will get back to where we need to be shortly. Okay, there we are. So then we plug all that into our calculator. So let me run away and do that. And that's what I get when I come back. Right, so it's just a long slog on the calculator. 0,20416 blah blah blah, whatever, to however many decimal places we want. Let's just call that 0,2. So that's our probability for the first one. And so it's going to go for each of these. Now the last one, we're going to have to, not think, but we've got at least a slightly quicker way to do it. So I'm going to rub out these paths now and say, let's look at our paths to make the next thing work. The probability of drawing at least 2 aces. So, well, this actually brings up something interesting, and that is we could get an ace the first time and then an ace the second time. Then it doesn't matter which of these 2 we go down. So I'm going to just kind of stop at that point to say, well, it doesn't matter which one of these we go down. So you're going to see how I'm going to write that in a second. And the other option that we've got is, if we've got an ace, then we must go not ace and ace, right? We can't go ace, not, because we need at least 2. So we could have 3, we could have 2, we could have not an ace, but then we must get 2 aces in a row, because otherwise we'll have not ace, not ace, that'll only be 1. So we've got kind of 3 or 4 different parts. Now, I just want to focus on this first bit over here. That is to say, well, this first path here, so let's go for, that's kind of our first path. That probability, I wonder if it's worthwhile just, let's take all this stuff down so we have it here and maybe a bit smaller for reference. So, goodbye, calculator. So in that first path, we're going 4 over 52, times 3 over 51. Now, instead of splitting this up and going times 2 over 50 plus 4 over 52 times 3 over 51 times 48 over 50, we could do that, but this is going to capture both of those paths. Plus, or we could go 4 over 52, so that first path, 48 over 51 times 3 over 50. Or, so another plus, we've got, I don't know, let me move over there. So, or we've got our last one, 48 over 52 times 4 over 51 times 3 over 50. Okay, and so we put all that stuff in our calculator and we get some merry answer that I'm hoping you're going to check. And I'm just going to look back at my sheet and go 0,013, 0,013. So not that probable, as it turns out, to get at least 2 aces. Okay, so, and yeah, much less possible than getting exactly 1. Okay, I just want to unpack this bit over here because I think it's useful to think about. Let's just look at that. So I want to look at the probability of going along, I can't drop that one out now, that's silly, of just going along this top path. So just that bit there. So let's screen grab that and take it down and replace this. Okay, so this we don't need anymore. And I'm just going to focus in on that top path there. So what I'm saying is, if you go there, there, and there, or you go there, there, and there, this part here highlighted in blue could have been split into 2. So we could have gone the first option, 4 over 52 times 3 over 51 times 2 over 50 plus 4 over 52. That first bit's the same, next bit's the same, times 3 over 51 times, and this time we go down the bottom path, which is 48 over 50. So if you feel more comfortable splitting that into its 2 branches, go for it. If that's going to help you rather just make sure that you always get that, then go for it. But if you do want the shorter method, you can go, well, if you get to this point, well, that times that will give you both of those options because those 2 added together must be 1. So you can check for yourself if you want to how you can factorize that out or use your probability knowledge to see how those 2 are the same. Up to you. As I said, I don't want to kind of overthink or overstress that, but it's just an interesting idea. Okay, that said, let's head into our third and final bit over here. So let's rub this bit out because I think we're going to need this space to do the third part. Ooh, goodbye. Go away. Okay, it's gone away. So here we go. We've got part 3. So this was part 2 over here, strangely enough. And part 3 says goodbye to you, and all these funny little dots. And says, what's the probability of drawing at least 1 ace? So now what we could do is this. So we must draw at least 1 ace. So let's start highlighting all of these. So we've got an ace. We could have 3 aces. We could have an ace, ace and not an ace. We could have an ace. We've done that one. Ace, not ace, ace. We could have ace, not ace, not ace. We could have not ace, ace, ace. We could have not ace, ace, not ace. We could have not ace, not ace, ace. So we could add all of those things together. That plus that plus that plus that plus that plus that plus that. Or we could make our lives a whole lot easier and say, goodbye. Let's consider the one route that we can't take. What we can't do is go not ace, not ace, not ace. So if we find what that is, well, all of these things need to add up to 1. So therefore, if we go 1 minus what it can't be, we'll get all the rest. So that makes our life a whole lot easier. That one is a definite no-brainer that we need to do that. So we're going to look at the probability of getting at least one ace is going to be 1 minus the probability of getting, I'm just going to write, no aces. So 1 minus 40, there were 48 non-aces out of 52. Then in the next draw, there were 47 out of 51. And then there were 46 out of 50. And so we can punch that into the calculator to get 0,217. 0,217. That's quite a, I don't know, not a high, but, over 20% chance that you're going to get at least one ace when you draw 3 times in a row. So that is that. And as you know, we need to head back.